Yeah. So basically, the point is that we are trying to get a Cauchy criteria for convergence. Okay. In this case of functions also, we know a criteria in the case of sequences. We want to get that in there. But let me just say that for the sequences thing, we know that this is the same thing as an converges to some limit, some number L. Fine. That is true, right? Now, let us see what happens in this case. So, yeah. So if I say that, let's say that we have this limit fn x n tend to infinity equal to fx. What does this mean? This is a pointwise thing that for every point this happens, every x this happens, right? I can write this, but it's understood. This is not uniform. Okay, every x this happens. Does this imply that fnx minus fmx, yeah, is less than epsilon for all n and m bigger than or equal to n, yeah, no, given epsilon? Does this imply this? See, I'm not asking that this should work for all x, yeah, but I'm saying that given epsilon and given x, I'm not asking uniform. I'm just asking if this happens.
Yeah, we
Obviously,
can just plug it into that.
Yes, I mean that is just the because this is just the real number. This situation is just real numbers, right? I mean, this is just a sequence of real numbers converging to a real number fx, and then it's Cauchy. Everybody knows that, right? And obviously, the converse is also true, because again, same thing, right? Because a Cauchy sequence converges because these are just numbers, right? Because the x is really separated out, and you can understand this is not such a good definition. But in this case, Cauchy convergence is the same as convergence because where everything is happening pointwise, there's nothing to really say. Okay, but now if we say that this is, so let me not use limits here. Let me not say the word limit. Again, the language of the soup norm makes everything more elegant, but it's okay. It's good to just say things in a more elementary language. If this converges uniformly, and whenever it's too uniform, I will not write x. Just I think that's a better thing to do because the whole function is kind of convergent. In this case, can we say that it is that this happens? What happened? Oh, that recording got completed. It's there. So if the convergence is uniform, then can we say that the sequence is uniformly Cauchy? This is called uniformly Cauchy. Given epsilon, is there such a capital N such that for all x, the terms are less? Yeah, one capital N which works for all x. So is this true? Is it uniformly Cauchy? Or this is the same as saying under the other thing that we had said yesterday, now we don't have to say x and so on because that definition is supremum of the difference. And if that is less than x, then everything, but one doesn't need to know this. So, you see, is the question clear? Yeah.
Can you
this
repeat
is
the question?
Yes. So see, we have uniform convergence. Given if we have uniform convergence, Fn is converging to F uniformly. You know the definition. then we are wondering if there is a similar Cauchy criteria. So what should the question be? If there is uniform convergence, then is this sequence Cauchy? Meaning that sequence Cauchy in the uniform sense, meaning that given an epsilon, is there a capital N so that for all n and m this is true for all x? That capital N should work for all x. That's the uniform Cauchy, right? So does the first uniform convergence imply uniform Cauchy? So the question is, I mean, we should want that, right? This should be true. This should be a good thing to be true.
Yeah, I guess
Uh-huh.
yes. When it is uniform, you get a k, right? And
You mean
like
here in from the condition?
yeah, you get a k basically.
Yes.
And if we can take m and n greater than k, then basically we take yeah, so we can take fn is yeah, for greater than, and we can take f m of x minus f is less than the same epsilon for m greater than k for all x,
Right. So
and then we can just perhaps add them.
yes.
So basically epsilon by 2, we add them, we get epsilon, and then we can just use the triangle inequality on the LHS side to get a lower bound, lower, yeah,
Yeah.
and then so the LHS is lesser than fn of x minus fm of x.
Yes. And since it was true for all x, you can use the triangle inequality for all x, right?
Right.
Yeah. Then we're done, right? And the 2 epsilon, you can make it epsilon. Easy. This is easy, right? It should be true and it is true. Now the question is the reverse also true? If this direction is true, it happens in any metric space. What did you use? You did not use anything particular about this, right? I mean, you just use the fact that this norm,
Because
this thing is
while
sort of like
estimating the metric, we ensure that the metric follows triangle inequality.
the standard things, triangle inequality, and
So
that's right.
basically, in spirit, it has to follow this.
Huh. Yeah. That's good. So this is okay. But now the very important thing, the all important thing is the reverse true. Yeah, it's the reverse true. That will be very important. Yeah. So just think about this. I will just come in a minute. Okay. So Okay, sorry. Yeah. So is it? So is this true? This is an important question. Cauchy convergence implying convergence is a very desirable thing. We have a definition for such spaces or places where it happens. We call them complete. Okay. Yeah, that will be an exercise. So what do you guys think? Yeah. Is it, will Fn converge to some, well, will it converge to some F uniformly? Well, forget about uniformly. Let's first see if it converges to some F. Does it converge to some F? Yeah, it does limit exist? Does this exist? Does it even exist? I mean, that's the first question. Does it even pointwisely converge for all X? Otherwise, we cannot even go forward, talk about uniform convergence and so on, right? Well, the answer to this is yes, because again, this is just a question of real numbers for all X, for each X, right? And for each X, there's a Cauchy sequence of numbers, Fnx, right? For every X naught, it's a Cauchy sequence of numbers, and Cauchy sequence of numbers converges. So the answer is yes. So there is a F that is true, right? So is this point okay? That there is a function where it goes, right? Because for each X naught, yeah, is it clear? If it's clear, then someone should explain me. Then it will be better.
Yeah, it's yeah.
That is
clear.
easy, right? Okay. All right. Anyways, not clear, you tell me. Okay. So what I'm just saying is we can now write that there is a X. Now we want to say that this Fnx goes to this F uniformly. Now we want to get uniformness.
Actually, can we just draw something because it aids in understanding?
Yes. Yeah.
Because so in my book I have drawn a graph. I've drawn a band.
Band meaning one or many?
No,
Many.
band in the sense like the epsilon band I have drawn.
Oh, yeah, sorry. Okay. Yes, right. So that's a good thing to do, right? So there is this epsilon band, but epsilon band around what? That is the question. Yeah. I mean,
Yeah.
because it's not a, yeah, that's the, because the function
Then
can go up and down and, but it's fine, right? It's right. I mean, let's just say that there
for
is,
two epsilons, for two functions, we can obviously draw a particular epsilon band.
yeah, no, what I would do is I'll just draw one function, this limit, and around this we can draw an epsilon band. Why not? That's the best, good thing to do, right? So let us just draw an epsilon band around this. So it would also like just follow the function, right? One upward and one downward. That's the epsilon band, right? Like this is, I mean, this is your epsilon, 2 epsilon, 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 right? That is, and around F I'm drawing because why? That's around which you have to draw, right? That's the right thing to do. So can you put in all the functions inside that band after some n? That is the question. Yeah. So if let's say that you,
But we
sorry,
can draw another diagram, right? Like just on to the left side of this diagram.
Okay.
We can draw another diagram by the what does this statement mean by this is a Cauchy sequence, right? So maybe draw 2-3 functions f1,
Yes.
f2, f m, f n, f l.
Yes. Okay. So let's say,
Just draw 3 functions.
yeah, right.
And perhaps we can take another color, green, and
Hmm.
draw the epsilon bands for, let's say, 2. Take 2 at a time. So
Okay.
f1 and f2 we can draw a band,
Uh-huh.
and then f1 and f3 we can draw a band.
Um. Hmm. Right. So that band has to be around. Yeah, but that has to be the same band, right? Around
Yeah,
f1.
no, I'm saying that the
But like if you take, yeah, so for f1, f2, and f1, f3, the band will be
I'm
same.
saying that the bands must themselves be behaving in certain way.
Certain
Like when
way.
you draw them, they are like, obviously when you want the left hand picture to somehow look like the right hand picture.
Yes. Yeah. So after a certain, yes, I mean, yeah, that's right. Yeah. So eventually those two pictures should look the same. Yeah, that's right.
Basically what, like after drawing many of these diagrams, what I have realized is, like, I think is that the red band which we have drawn, all the other green bands must be contained inside the red band somehow.
No, I don't agree with that. That is a difficult thing to say. Because yeah, that's a little not so great. But you see, this should be true, right? Because I mean, if 2 points, I mean, if these two functions fn and fm are not are very close to each other, right? And if fn, yeah, if fn uh, is tending towards fx and fm is also tending towards fx, and fn and for each x, right? Then how do you establish the uniformness?
I don't see why my claim is wrong, because
Hmm.
you just now, right now you said that fn and fn must, if both of them must converge to f, then obviously they must be contained inside this red band, right?
Yes, but their bands need not be contained inside the
No,
red
but
band.
why I don't
No,
see
because
how.
they
Yeah,
could be very
okay.
much on the, yeah.
Outer side, yeah.
Ah,
I
Then you have to take an epsilon by 2, and then you can say that their bands would be contained in the, then that will be true. You see, right? I mean, if you take it like more in the interior, if you take epsilon by 2 or 4, whatever, then it will be true. Yeah. No, but this statement is true, and the proof is not difficult. Okay. So I can say the proof now, I think, but let me not say. Why don't you guys think about it? Because let me just say that it is true. Okay. Yes, so this is true. So one way in which you can go, which I just thought of now, there is a traditional way, but one way is that, I mean, why don't you assume that it is not uniform, right? So let's say that you get that for every n, there is a xn, right? For each n, you have an xn, so that it is outside the so that fnx is outside the epsilon band, right? And then you get this infinite sequence of no, so 1 minute, 1 second. No, so what am I saying? This is not the usual way to do. There is one easy way, but if you want to go by contradiction, so if you want to go by contradiction, it's just an idea here. Otherwise, you try. There is a very straightforward way also. But if you want to go by contradiction, suppose it's not uniform. Okay. So if not, if it is not uniform, then what does it mean? Yeah. It means that for some epsilon, that epsilon is fixed. Okay. It fails. And so for some epsilon, there is such that for any n, yeah, there is a no, so the way I should say it, for any n, there is a xn, yeah, so that, no, 1 minute. So any n you take, that n does not work, right? And what does that mean? That n does not work. It means that there is some xn, so that xn creates a problem, which means that this distance is more than epsilon, more than equal to epsilon, right? If the convergence is not uniform, then for all n, the thing fails. So you take any n and the thing fails. What does it mean? I mean, it means that there is some, yeah, no. So for any n, no, so sorry. For any n to take, just a second, fn minus f may work, but then there will be something bigger than that which may not work. Yeah, so this is not to say this n, for any n you take, it doesn't work, which means that, there is some m, which again is a function of n, right? Some m for which it fails, right? Which means that there is some nm, right? That m, let's say that nm, that's one of the functions, yeah, after that n fails, which means that there is some xn for which it fails, otherwise it would not fail, right? Something like this. And using this, you can contradict the Cauchy criterion S. Right? Using this, you can try to contradict this Cauchy condition. Let's see. Okay.
So what if we just set m as f of x? Like if we say m tends to infinity.
N tends to, yeah, so that's the usual way to do it, right? I was just exploring the non-usual way. Yes. I mean, that's a better way to do. I should not use usual, whether you know or not, I don't know. But yeah, that's a better, easier way. So yeah, think about this homework. There is still a few things which you have to write. So, but this was just a different idea. So Yeah, that's the easy way. But the point is that in the end, this is true. That's all I wanted to say. Okay. So we have this notion of convergence, or you could say that we have this notion of distance, which is between any two functions. The distance is the greatest distance. That is basically what the distance we are continuously talking about, right? That's why we are saying for all x, this must be less than x, which means that, you know, if the distance is the greatest distance, then also, yeah. So under that distance, this every Cauchy sequence converges. Every Cauchy sequence of functions converges. So we have shown that under uniform convergence, every and this is a very important fact. I mean, in general, Cauchy sequence, this happens in reals. I mean, every Cauchy sequence, which is like under the uniform sense, which we have defined, or from the soup metric norm also, you can say that sense. In that way, you can say, but I've defined what uniform Cauchy means. Yeah. So every uniformly Cauchy sequence of functions converges, right? And then the fact about real numbers is a special case of this. You can take constant functions, but obviously we have used that. So that's all that property we have used. So it's true for real numbers, and it's also true for collection of functions if you introduce this sense of, and that's a similarity, one similarity that we have established between these two things. Okay. Now, any system, any place where Cauchy sequence converges, that system, that set, that metric space or topological, not topological space, is called complete. Okay, it's called complete. Now, for real numbers, try to show this, and then it will be true for any, same proof will work for any metric space, but for real numbers, try to show this, that, or rather show that Cauchy Cauchy implies convergence. Yeah, I mean, this property of real numbers, right? That every Cauchy sequence converges. This property of real numbers, let's assume this for a minute. Okay. Show that this implies that in reals, every set, I mean, every bounded set, naturally, we'll see every set has a supremum. If it's not bounded, then it's infinite or whatever, but every some things, but every set has a supremum. So, I mean, this is something that is usually done first, that every set has a supremum is sort of proved or assumed or whatever, and then we prove Cauchy criteria much later. But I'm trying to say that Cauchy criteria is this fundamental. It is so fundamental that if you know that, if you use this thing that every Cauchy sequence converges, then you can use that to show that every bounded set has a supremum. So it's equivalent. Obviously, every bounded set having a supremum is what you use to show Cauchy convergence. If you really try to do the proof, that's all it is. But anyways, leave that. If you don't, means that's not, you cannot remember everything directly, but try to prove this. Try to prove this. This is a very, and the same proof will work everywhere, but just prove this. Okay. So basically, this Cauchy condition is very, very fundamental. Let's just leave it at that. There are some, it can be made precise in what sense it is fundamental. It can be used to construct the real numbers from the rational numbers. But let's just prove this. Okay. This is your homework. And the previous, so there are 3-4 things that I've said, which you should try, and also try more problems. There is a lot of time for 1 week. Do ask me if you have any questions. And yeah, then that is it. Then we'll meet next Wednesday, 9 p.m. Same time. Hope you will have some interesting questions so that I can try and see. And okay, that's it. Thank you.
Sir,
Yes.
sir, yeah. So there is this update that, yeah. So the results were out today.
Huh?
Yeah. So I didn't get it.